All right, you can see full screen at least. Thanks for your patience. Sorry about the technical glitch. So let's get started with flash memory, right? The first slide will probably make a lot of sense to you because I'm sure at some point in your life, you must have seen either one of these two memory storage devices. These are mainstream, right? On your right, you're looking at a conventional hard disk drive. And on the left, it's SSD. It's more mainstream now, but 5 years ago, it was very expensive and only a few select devices could have SSDs, right? Even nowadays, most cheaper laptops will not have SSD. They will charge you extra to go for SSD versus hard disk drive. So in a hard disk drive, we used to have a moving component like this. You literally had a disk, magnetic disk, and you had a reading head, magnetic reading head that used to go in places to read data magnetically. So as you can imagine, there is a lot of mechanics involved. Something has to rotate and then go and magnetically read out the data. It has to be really slow. And that was exactly what it was. Although we still use them because they're super cheap compared to the other options, but they're not the best solution for our modern day standard. Okay. On your left, you're looking at, as the name suggests, it's all solid. Nothing is moving here. It's SSD, solid state drive. And the solid state drive is made out of flash memories, which we will be discussing today. All right. Let's talk about it. Like very quick history. I love talking about how things come into being. So it was invented back in 1980, so that you know how old this technology is. More than 40 years old, right? It's older than all of us, don't you think? All right. So it's a really old technology and still being used. So that tells you, I keep telling you that you are basically living through a generation where things will dramatically change. So flash memory has had its time. DRAM, SRAM, like we are basically almost tired of looking at this conventional stuff and just trying to incrementally improve their performance. We have to have something dramatically different moving forward. Okay, point of inflection that we're looking at. Okay, so he was an engineer in Toshiba. Uh, you must have heard about the company, right? It's a Japanese company, and back in 1980s, he invented the concept of flash memory, and it took more than about 15 years to commercialize. So it's okay. Idea to commercialization, more than a decade. And then Intel, notice there are two types of flash memory, NAND and NOR. The first one that was commercialized was NAND, and the other one that Intel commercialized back in 1998, 3 years down the line, was NOR. And I'll discuss both types very quickly in today's lecture. Okay, so this is the very basic concept of flash memory, and I hope it will be easy for you to understand without me drawing anything, but if there is a need, I can draw on top of this, right? So let's try without scribbling. Let's try with just with words. Look at this structure on your left. This is a transistor structure, don't you think? You have source and can you see my pointer? Okay. Let me see if there is anything else that I could bring up. Anyways, looking for the, yeah, there you go. Laser pointer. Is it better now? Can you see? All right. So you have a source, drain, vice versa, and then this is the gate stack. Very conventional MOSFET structure. Oh, wow. So what's the big deal? What's with all this flash memory? Like, it's just a transistor. Can you look closer? Do you see a difference here in the gate stack per se? Two levels, basically. We still have one gate, but yet you're right. we basically have two levels within the same gate. So we could categorize it as two gates. One of them is floating. It's not connected anywhere. Okay. The other one, the control gate, is the real gate that most transistors have. It is connected with external metal and blah, blah, blah. But internal gate, the floating gate, is basically buried between two oxides. So you have a blocking oxide, you have a tunnel oxide. Can you read this? You have a blocking oxide and a tunnel oxide. All right. So what is it doing there? And that's exactly what I'm going to discuss next. Okay, this floating gate is the zone where we store information. So this floating gate is kind of like a capacitor. It's not, remember, it's not, but I'm just making it up. Imagine in DRAM, we use a capacitor to store charge. So instead of using a capacitor to store charge, if we could use a different reservoir to store charge, that was the idea. Okay, capacitors leak. I mean, that's why we have refresh and whatnot. That's not non-volatile. The moment you remove voltage, capacitors will just leak away all the charge. And there you go. It's non-volatile. It's volatile, right? So how do you make it non-volatile? Why don't we make it in a way that we will trap the charges in a zone from where they will not be easily able to get out? So you basically like put them in a prison, put the charges in a prison, kind of like that. So imagine these oxides are insulated. If you somehow find a way to trap some charges in the floating gate, in both sides, there is no way for them to go because they are all insulators. So these charges will be basically trapped in the floating gate. You guys all see that? Even before we get to the next slide, I want to cover the concept, and hopefully it will make a lot of sense when you go to the next slide. How many of you remember that in MOSFET, the threshold voltage is affected by the charge at the gate? Do you guys remember that? Where did we discuss this concept? So if you have a positive charge at the gate, somehow stored, that affects the threshold voltage. Thank you. In ferroelectric memory, remember that was the whole point of ferroelectric memory. When you make ferroelectric layer positively charged or polarized, it affects the channel in a way, versus when you make it negatively charged, it's affected in a different way. So your threshold voltages will be different for positive and negative charges. You already have this idea in mind that if there is some sort of fixed charge trapped in the gate level, gate stack, that changes the threshold voltage. The only difference is this floating gate idea, is basically doing the same. It's trapping charge in the floating gate. And when it is storing the charge in the floating gate, that affects the threshold voltage. But when there are no charges, you have the regular threshold voltage. So if it is regular threshold voltage, one memory state. If it is a different threshold voltage, a different memory state. There you go. Same concept like ferroelectric, except we don't use ferroelectric here. Ferroelectric transistor-based memories are more recent innovation or proposition, by the way. So this dates back to 1980s. We didn't have a better way of doing things at the time. All right. And by the way, the reason why it survived the test of time is because it has a lot of favorable property that ferroelectrics don't yet provide. I mean, you could have just replaced this with a ferroelectric transistor. But remember, deeper down, endurance, reliability, all those questions have to be answered. Okay. So let's not get ahead of ourselves. Let's move to the next slide. So what I just explained to you was you have to put some charges in the floating gate, but I didn't tell you how. Exactly how are you going to do it, right? So let's see. Take a look at the transistor structure, and please let me know if you cannot see it. Okay, I will zoom in. So this is your source and drain, like usual. And imagine you apply a positive voltage to the drain. This is basically a transistor. When you apply a voltage to the drain and source, you have electrons flowing from source to drain, right? The only difference here is, okay, what if you somehow supercharge the gate, like apply 10 volt, positive 10 volt, like really, really high voltage. Remember, there are two electric fields acting on the electrons. The electric field between drain and source that's pushing them laterally, and there is an electric field vertically from the gate. The reason why electrons go this direction is because of the oxide. It's an insulator. It wants to go, but then, oh, okay, there is no way I can go there. Unless you have a lot of motivation, like literally, like I will give you $1 billion. Will you? Something like that, okay? So that level of motivation, and that's basically $1 billion for electrons, 10 volt positive. It's a lot of motivation. So even this oxide barrier cannot stop the electrons because electrons can do what? Tunnel. Well, it's just about how much energy it needs, how much motivation it needs. If you apply really high voltage, you can make these electrons tunnel through the oxide. And once they tunnel, they get stuck here because of what? Okay, it's one thing to tunnel once, and then you have to tunnel again. Man, I have had enough. Like, let me rest now. And obviously, you can handle that by making this really thick. Tunneling probability reduces exponentially with thickness. If this oxide is thinner, it is easy for the electrons to tunnel and get stuck in the floating gate. But the next oxide could be really thick. And that means you don't have further tunneling and it doesn't really go away. It gets stuck in the floating gate. Isn't that a simple concept? It's from 1980s. What do you expect? Right? All right. So there you go. Once you do that, you have a layer of electrons that is a fixed charge. Compare that to negative polarization in a ferroelectric. There you go. Same concept. Next time, when you turn on the transistor and there is a current flow, you'll see difference because the threshold voltage will shift. Are we all good? And yes. Yes, that's a great question. Typically, they can be the same oxide, but don't quote me on this because there are companies, the flash memories are being made by so many different companies. Nobody stops me from trying out, hey, what if I use different oxides? And honestly, I'm sure companies have tried different oxides and they will not tell you. These are mostly proprietary information. What I can tell you is the concept. It's not patented. What is patented is the exact composition of the oxide, exact thickness of that is unknown to even us. If I'm just a tangent here, if any of you join one of these memory makers, they will make you go through a training for the first 3 to 6 months, and then they will tell you the internal details, and they will obviously have you sign NDA so that if you ever talk about it uh, outside the company, they will sue you like $1 million or more. So you see the point? These questions are obviously great, and you're right that we could use two different oxides or we could use the same oxide. The concept remains the same. Maybe one will help with performance. And I have a slide which will talk about a coupling ratio. And I'll probably relay back to this question and I'll tell you how using different oxides could help with coupling ratio. Okay, remind me if I might kind of skip it, but I'll try to make sure that I covered it. Thank you. Okay, so let's get to the next. All of these have been discussed in detail in text. You can read it at home. These are there for you as a textbook kind of thing, so that you don't have to read any textbook because there are none. Okay, all right. So moving to the next one. On the previous slide versus this slide, it looks exactly the same, don't you think? There is a difference in the title. Here it's Fowler-Nordheim tunneling. On the previous slide, notice it was hot electron injection. What do I mean by that? Notice, just look at the animation first. Electrons going through the channel, gate attracted the electrons, and electrons just tunneled through and got stuck. But remember, very important point here, electrons were moving along the channel because drain called them to. So they were in motion. When electrons move, they have a kinetic energy. And when electrons have kinetic energy, we call them hot electrons. Engineers came up with this thing. Okay, they're hot electrons when they're moving. So there is a difference. When electrons are moving, imagine there is a moving car. It's basically racing at a high speed. All on a sudden, it got derailed. Maybe black ice or something, right? It got derailed. But all those speed that it had, the kinetic energy, will then factor into when it hits something, it will be a more serious hit because the kinetic energy will be converted into other energy. Do you guys all agree with it? Energy is conserved. But imagine if this was just a car sitting along, just sitting along, and somebody attracted the car with some magnet, the car will just go towards that magnet and just get stuck. But then collision will be more benign. Do you think that? Because there is no kinetic energy to convert. Do you guys all agree with it or not? I guess, was it too much with the analogy? So when electrons are moving, if you try to attract them into the floating gate, they will go, but they will bring some extra energy with them. Keep that in mind. But the other approach would be, notice this drain and source are floating. Notice this is float. So they're floating. You basically just electrons lying around here and you attract them, they get stuck. Typically, that's a slower process because what you rely on is minority carrier generation. I'm not getting into the detail of it. But basically, you wait until the electrons come and show up here and create a bridge. That's all. You don't channel them from here to there. They just come and just gather around, and then you just grab them like this. Okay. So there are two reasons why both of these approaches are used, but this one is obviously slower. The hot electron approach is faster, but we have to use them for certain scenarios, and I'll probably get into that at some point. But now there are two ways to do it, using hot electron based injection or Fowler-Nordheim tunneling based injection. Both are tunneling, by the way. One of them is hot electron tunneling, or the other one is Fowler-Nordheim tunneling. Okay, so why did I tell you that use that analogy of car being on motion and then sliding ahead and then hitting something with causing more damage? Because that's exactly what electrons do, by the way. It's It's faster to catch hot electrons, but it is also more dangerous. When these electrons get into the floating gate through the oxide, they hit the oxide bonds and they create damage in the oxide. Over years, these broken bonds can lead to performance degradation. So that's what lead to endurance problem. How many times can you read and write? Because every time you write, you damage something. Am I making sense? So this is like secondary concern. First, you come up with an idea. Oh, this is fascinating. Then you come up with a prototype. Oh, that works. Great. Then you sell a product. Wow, that's awesome. 3 years later, people start complaining. Hey, it's not working anymore, like blah, blah, blah. And then you realize, oh, that was a reliability problem. Okay. But at least for the first few years or so, it's all nice and cozy. Okay. So moving forward, what I showed you so far is called programming. So when you put the charges there, in industry, they call it programming. Obviously, the opposite is erasing. How do you get these charges out once they're there? How do you do so? Remember, you have to get them out through the same oxide as they came in through, because that's the more reasonable oxide that electrons can tunnel out of. Tunnel in and tunnel out, not the other one. Okay? So it's basically you do the opposite. You attracted the electrons with positive charge. Now you basically repel them with negative voltage. So one way would be to just apply negative voltage here, but practically what we do is we make this ground and apply 10 volt to the body. Don't forget the MOSFET has a body terminal, right? So this body terminal has 10 volt. So now this electrons will be attracted in the other direction, right here, right? It's quite opposite electric field, and they will just tunnel out and get back to the channel again. Now you have flushed them out. That's erasing. Isn't that simple? No fancy spintronics, blah, blah, blah. Super simple, plain vanilla stuff. Okay. All right. Now, this is what we get. Did I tell you that when you have charges inside, threshold voltage changes, right? So notice, this is your ID versus VGS characteristics that we saw before as well, in the ferroelectric lecture, at least. This is the transistor when you don't have any charge. This is your threshold voltage, because that's where the transistor turns on. What happened here? This line corresponds to when you have trap charges. Okay? Trap charges. So basically, your threshold voltage increases. By the way, this is considering NMOS. If it were PMOS, it would be exactly the opposite. But you get the point. Okay? Doesn't matter. You have two threshold voltages. That's what matters. But take a look at both of them side by side and figure out a way to sense the stored data. How do I know what was being stored? I cannot go and check out whether there are charges trapped in, right? There has to be an electrical way of sensing. Here is how. When you read, you apply a voltage around this much. Imagine there are no stored charge in the trap gate, in the floating gate. So then you get the current out of this blue curve. You guys all agree? You get a higher current. But if there were floating charges, then you are operating in the black curve. So for the same voltage, you don't get any current at all, or like very few. Does that make sense? So just looking at the difference in current, you could sense. And isn't that the story everywhere? Even for ferroelectric transistor, that was the exact same story. For positive polarization, you have some current. Negative polarization, you have different current. One of them is less than the other. Sure, you have a reference to select, to sense. Exactly the same concept. So in fact, the ferroelectric transistor concept tried to replace flash memory. Why? I mean, I don't have to tell you why, because remember the voltage levels here could be 10, 20 volts. And we are living in an era where people talk about 1 volt, 0.5 volt. So 10, 20 volt is like, okay, it's really pushing our batteries. Okay, so that's the reason why people are going with ferroelectrics and others. All right. Are you guys all good so far? Okay. What does this one mean? And I covered this concept many times. When I say that you have a threshold voltage for the transistor and you have a threshold voltage with charge trapped. So there are two levels of threshold voltage. Do you guys all agree? I just need to put a reference in between. I will repeat myself again. There are just two levels of threshold voltages in the flash memory. One without the trap charge, the other with the trap charge, and I just have to put a reference. Is that right or wrong? Just look at this and probably you'll remember. I can never say that there are just two levels because there is always what? Variation. Okay, how if I have 5 more electrons or 5 less electrons trapped, can you count electrons? Like, okay, come, give me 12 electrons. Like, can you do that? There will always be variation, don't you think? Okay, so that means since you cannot control it to that degree of resolution, there will always be variation. There will be, in a conventional structure without the trap charge, you have a range of threshold voltage, which is like this. You have a range. There is always a range. Remember, in electronics, there is never a level. There is always a range. Unless you're dealing with something super duper fancy, like a topological insulator. Anyways, look them up. They have absolutely zero variation because of quantum mechanics. Anyways, so conventional semiconductors will always have variation. No level will be absolute. There will be a range. So you have a threshold voltage when you don't have a trap charge. You have a range of threshold voltage when you don't have a trap charge. All you have to do is find a middle ground as a reference. That's all. That's more realistic. Okay. Let me move to the next one. There comes the concept of coupling ratio, as I promised that I'll discuss the other concept. Let's visualize this together. Can we? Please pay attention to this. Notice this node represents my floating gate. This node represents my actual gate, the external gate. So remember, there are 2 oxides. And wherever there is oxide, there is a capacitor. You guys agree? If you have oxide sandwiched between 2 metals, that's a capacitor. So in this flash memory, you basically have 2 capacitors at least in series with each other. Okay. So there you go. One capacitance. And these are other capacitance. Basically, this is the body capacitance of the MOSFET between the gate and the body. But there are also overlaps from the source and drain. Source overlap, drain overlap capacitance. Okay, if you remember 335, a MOSFET has capacitors everywhere. There is gate to source overlap, gate to drain overlap capacitance. So imagine the CS and CD are like that. Okay, so if you look at the capacitive channel, this is how it looks like. And to make it operate, to make the flash memory, to program the flash memory, you have to make sure you have sufficient voltage showing up at the floating gate, because that's where all the action occurs. You don't care about, you don't care that much about the other gate. You want to make sure the floating gate has enough voltage. Hear me out. Hear me out. Look at this structure. There is an oxide here. There is another oxide here. When you apply a voltage, this voltage will be divided across 2 oxides, the top oxide and the bottom oxide. Okay? Imagine you apply 10 volt. The top oxide takes 9 volt. The bottom oxide takes 1 volt. Will it be useful? Simply by using 10 volt, you cannot excite the electrons because electrons will not see 10 volts. Does that make sense to you guys? So who determines it? The relative capacitance of these 2 capacitors. Remember resistive division rule, R1 and R2, that we also dealt with capacitive division rule. When you apply a voltage across 2 series capacitors, they take a share of the applied voltage. Remember negative capacitance discussion, we discussed that? Okay. So you have to design the top oxide and the bottom oxide in a way to do what? To make sure most of the applied voltage comes to the floating gate. Are you all good? Okay. And this slide tells you the math. Basically, very simple. Just what is the equivalent capacitance of 3 capacitors, folks? Just some of them. Okay. And then when they're connected in series, basically this is the capacitive division rule that you get. So this tells you the voltage that you will get at this node compared to what you apply here. And this ratio represents the efficiency of the overall gate stack of the flash memory. Okay. The higher the coupling ratio, the better it is for you in terms of energy efficiency. So how can you handle the coupling ratio? See, these individual capacitors have a role. Can you not use a high K oxide in one of them and low K in the other to change their capacitance? Obviously, that's a design choice. And that's why I can use hafnium oxide as a high K and silicon oxide as a low K in both. But that means, remember, anything has a big ask, which is fabrication. So basically, can I handle the expense? Hafnium oxide will have to be made by a different process than silicon oxide. You cannot make them in the same place. I can make a design choice, just a thicker silicon oxide, thinner silicon oxide, or hafnium oxide, silicon oxide, if you can afford it. Okay. I cannot definitively say that nobody is attempting multiple oxides, but I cannot even tell you that they are, because it could be a trade secret. Are you guys all with me so far? Okay. So moving forward, the concept of NAND and NOR flash. We'll start with the concept, and don't worry, I will not rush through this. I will get back and cover it thoroughly again, but I want to familiarize with you at least with the terminology. What does it mean to have NAND? What does it mean to have NOR? Okay, folks, listen to me. Have you guys seen a NAND gate ever? Have you designed one? In a 2-input NAND gate, NMOSes are in series. 3-input NAND gate, NMOSes are in series. If you have 4-input NAND gate, they are always in series. NMOSes, and we are dealing with NMOSes here only, not PMOS. Okay, if there is a choice between N and P, always go with N. That's the no. Okay, easier to handle. Electrons are easier to deal with. Okay, number 2. Have you seen a NOR gate? What happens to the NMOS branch? Are they in series or parallel? 2-input, parallel. 3-input, 4-input, doesn't matter how many inputs. It's always in parallel. Exactly that for flash memory. That has to deal with the array structure. When you design the array of a flash memory, and there are reasons, I will explain the reason in great detail. But for the time being, keep that in mind. There is an approach where we put all these flash memories in series with each other in every column. Okay, so in a column, they're literally physically connected. So this is a symbol of flash memory cell. Notice there is a difference between these two transistors. Do you see that? Is that visible? The top level and the bottom level are regular transistor, not flash. And simply because there are 4 doesn't mean there will be 4. There could be 16, there could be 64, there could be more. Okay, this is just a representation. But there will be a chain of flash memories, all connected in series with each other, like a NAND gate. That's why it's a NAND flash memory. Okay? Are you guys all good with me so far? Okay. I'm gonna fast forward and show you the NOR as well, and then we'll get back to it. This is the NOR. If you see, each and every cell in the column will be parallel to each other, exactly like a NOR gate. It doesn't look like it, but let's do an exercise. But you have to pay attention because I cannot draw. Okay? Can you hear me out, please? Okay. When do you know that 2 entities are in parallel? If they have 2 common nodes. 2 common nodes. Let's start node naming. Node naming, okay? You have to remember the names that I'm giving. Let's name it A. Okay, this is A. So this transistor has 1 terminal, which is A. How about this next flash memory? Does it have a terminal called A? Can you see that? Notice. Does the other one has a terminal called A? Does this one has a terminal called A? Yes, so all of the cells have a terminal called A in the same column. Let's see the other terminal. Ready? It's going to be complicated, but you have to pay attention. So the other one, let's name this B. B. If this is B, this source line is also B. This entire source line is B. You guys agree? Okay, is this transistor also connected to B? How about this guy? Here, tick, 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 this source line. B. Again, how about this one? Connected to source line B. So notice, it doesn't look like it because of 2D plane. It's difficult to portray. But all of these flash memories are connected in parallel with each other within the same column. So it's like a NOR. So simply based on the connection, one of them is NAND flash, the other one is NOR flash. And there are justifications for both. And I'm going to give you high level justification first, and we'll dig deeper into it. Don't worry. NAND flash, it's difficult to access each and every cell individually. What you do in NAND flash is we basically read a page. And let me go back here. Yes, this slide is important for you to understand the guest lecture. So to familiarize yourself, so we'll cover this. Look at the structure of a flash memory. Doesn't matter whether it's a NAND or not. The cells that share the same word line. Notice this is the word line, right? Running across the control gate. they're called a page. It's a standard term. It's rows. Instead of rows, we call them page. Okay, page. Then vertically, when you have all these interconnected transistors, it's called a string. And obviously, the name suggests it's a string. So string, page. And this entire array is called a block. This entire thing is called a block. So you have different blocks of flash memory, and there are pages and there are strings. So in NAND flash, we typically read out every page. So basically, when you read, we read the entire row at a time. And there are reasons. You can, with great difficulty, read individual cells with great difficulty, but it's not, useful. So we don't typically do it. Okay. But if you need individual control, then NOR memory is your option. NOR memory is faster, random access. NOR is faster. NAND is slower. But NOR requires unreasonable amount of area. Because of this parallel connection, just imagine it's a very complicated connection, right? Everybody has to be connected with everybody else in parallel. So you need a lot of contacts, and that create area overhead. So NOR memory is not area efficient. So the storage density of NOR is much lower than NAND. So when you need portable hard drive, do you need the fastest or do you need like 2 terabytes? What do you need, right? If you need more storage, that will probably be made with NAND. If you need the fastest possible thing, okay, like in your iPhone, for example, you need a memory that will work very closely with your processor and speed up the process. Sure, go with NOR memory. So both are useful, but NAND gives you better storage density, NOR gives you better speed. So no free lunch. Nobody gives you everything. All right, so you have enough information to understand the basics, right, of flash memory, I hope. And don't worry, we'll get started after this slide in the next lecture. Okay, we are out of time. So we'll start from the next slide in the next lecture, like after the guest lecture on Friday. And meanwhile, if you have questions, don't hesitate to reach out, okay? And you don't have to come to class to attend. Like I said, you can join from anywhere you want.